Okay, so I would like to start by thanking the organizers and for the invitation. And actually, I arrived yesterday. Our semester is just ending. And yesterday, I realized that this was a very bad idea to give this talk as for this audience because it's really hardcore experiments. But it has thinned down also, so I don't feel so bad in terms of the audience. So basically, I'll be talking about motion amplification with thermo-mechanically squeezed graphene resonators. So it's a very loaded title. So I'll basically, like first few slides, it's a 25-minute talk. So very quickly, I'll try to motivate what each of this means. But firstly, just in case if I lose my audience from the first slide, this is really the take-home message. What we are doing, there's a very large planar resonator or oscillator, simple harmonic oscillators in simple terms, which is basically like this yellow thing. It's a silicon nitride. It's a material-based oscillator. So you can just think of this as a planar like drum. And in between, there is a hole exactly like a drum, and there is graphene deposited on it. And when I say motion amplification, I mean that small induced motion in the silicon nitride resonator is actually amplified by the graphene's motion. This is the same image of the device. This is actually a work with Kirill Bolotin, and Ryan is a PhD student from University of Berlin, and Rajan is the PhD student and from our group. So it's a very close collaboration. Kirill's group is actually, they specialize on graphene transport, but this whole optomechanics kind of experiments are new for both of us, and we are learning basically along the way. So just the motivation, firstly, why do we care about amplification? And just because of the crowd, when I'm talking of amplification, I'm not talking of weak value amplification. I'm talking of experimentalist, like honest to God, like amplifier, just an instrument of amplifier. And of course, I cannot start about that kind of an amplification without Caves. And he said many things about amplifier, but this is actually a quote from his PRA, Physical Review A, 1982 paper. He basically says that, he summarizes that indeed the last essential quantum mechanical stage of a mechanical measuring apparatus is a high gain amplifier, and then comes his beauty. It produces an output that we can lay our grubby hands on. And then this whole question starts. This was all regarding LIGO, that when you're putting an amplifier, what is the noise you're adding, what is the minimum noise, and so on. So I'll also focus a lot, because I'm talking of an amplifier, on that. So, and then, all this from the first slide that I threw a lot of jargons, so why silicon nitride as the target resonator? This part, I feel that I really do not need much of an introduction for this audience, because there has been discussions on harmonic oscillators becoming a very important tool for quantum mechanics now. And silicon nitride really has been the leading candidate material for such room temperature quantum oscillators. And what really selects that, in fact, there's a very simple argument that, to see quantum effects at room temperature, you're talking of like two energy scales, the energy scale corresponding to the temperature and the energy scales corresponding to the oscillator. And this is quality factor, and this is basically, for theorists, quality factor is if I have a damped oscillator, as it's ringing down, it's a number of, oscillations it makes before it dies. So it's a number. So Q times h bar omega naught. And if you actually put the numbers for room temperature, it basically puts an experimental limit that Q times f naught should be of the order of 10 to the power 13 or 14. So that kind of tells you what kind of oscillator you should use for choose for f naught, and what kind of quality factors you are aiming at. Really, the field took off. People realized that it actually might be a reality from this. Actually, there were two back-to-back papers, PRX and PRL in 2016, very similar device, silicon nitride. And you see that this is basically a whole field of how to improve the quality factors. But this particular device, it's called a trampoline. It actually literally looks like trampoline. This white thing in the middle is basically the silicon nitride. You can see it's still quite big, 100 micron. And this basically, they saw like 10 million kind of quality factors. So you can see that 10 to the power 7, this Jack Sankey's group at Canada. And so 10 to the power 7, and with a frequency of megahertz, you're already starting to hit that limit. So really, this kind of took off. But nevertheless, you can see that these are like 100 micron, like 400, 500 nanometer thick oscillators oscillating in the middle. So they are very heavy. And as a result, simple half mx square is the energy, you know, so if the mass is larger, the displacements are very small, and that's where actually one starts thinking of on-chip motion amplifier to actually, you know, like increase the motion of these amplifiers. And there has been a lot of work, people just dedicatedly work on that. There are quantum point contacts people use, superconductive cavity. This is actually from Vibor's postdoc work right next door in ISC. He's now a faculty, you know, superconducting cavities. And there are other like room temperature microwave cavities, single electron transistors. People have also used like the same oscillators, higher order modes, and trying to use it. And of course, one can say that when I'm talking of like detecting and transducing motion, why I'm not talking of Michelson interferometer, particularly after LIGO, you know, like it is the instrument to use for, and of course we all use that to detect motion, but there are constraints of having a really low noise, quiet amplifier, quiet interferometer, because there are power requirements. Your shot noise basically scales down with the intensity. So you in an on-chip environment, it becomes very difficult. So these are all like towards pre-amplifiers. Like first you pre-amplify the signal and then you detect it. And we are basically proposing and demonstrating, hopefully, that that graphene actually can be a very nice mechanical amplifier. And why is that? Why I'm talking of graphene? Very simple. You know, this is another just take-home message for the talk, that it's basically the idea is very simple, that if you have a heavy oscillator oscillating, if you attach a very light mass oscillator, it will basically oscillate with a larger amplitude. So low mass, one expects high gain for the amplifier. You know, like the coupling I'll show, you know, it's actually very simplistic because the graphene is just placed on silicon nitride van der Waals, very strong, robust coupling. And that's kind of one of the issues that most of this pre-amplifiers suffer from. You know, they are basically extremely difficult. Like the device yields are very small because of this constraints of having strong coupling, and of course frequency tunability, broad bandwidth. So towards the end, I'll try to give numbers for all this. Hopefully I'll be able to convince you that graphene is a really good amplifier. Of course, there are very interesting noise properties, and that's what I'll be focusing most of the talk. So this is the device. You know, actually this gray thing you see is a silicon nitride. It's a very, very large membrane. I cannot, in this scale, I cannot put it really. It's actually a 350 micron by 350 micron device. And this is just an experimental thing. When you're putting graphene, you don't want to just have one hole with one graphene because the yields are small. So we actually have a range of tiny little like defects, 10 micron, 20 micron, and so on the same silicon nitride. And this is what I was showing you before, that, you know, this is a highly, highly zoomed in thing. This coral structure is supposed to represent a vibration of silicon nitride, this cartoon, and this we just go and focus on one of the graphene. This is the experiment that I'll be using for setup. You know, so it's a very standard, this red lines, you should think of it as a typical Michelson interferometer that's used. This sample is actually in a vacuum chamber. So this is the silicon nitride, this is the graphene in the middle. So what we do is that, so this is the membrane, which is kind of a complex membrane with this graphene in the middle. We actually, with a spacer, we put a gating chip in the back. It's just another conductive plane. The spacers are dielectric, so we can actually put a voltage. And when we put a voltage, it's a capacitor, but now the graphene is actually movable, so you can actually tune the frequency. I'll come to this more. So this is the part of that. And of course, a very important part of this is that, you know, you need to lock this interferometer to a very high precision through PID locking, and that's this piezo is for. And then there are this quadrature measurements and so on, imaging quadrature measurements. So this is a cartoon of that. You know, this is the spacer. This is the membrane, bigger membrane, actually in principle much, much larger, with a small little defect of 20 micron of graphene in the middle. So first, when we started with this, we have a confocal microscope. That's one arm of the interferometer. We go ahead and just focus on with a continuous wave light. And when we look at the spectrum, we started seeing these peaks. Initially, it was very mysterious for us for a week or so, but then we realized, you know, over the last 4 or 5 years, people have seen this, and it's quite an exciting thing. It's actually just the graphene, you know, it's in vacuum, but it's just oscillating. It's doing a Brownian motion because of the thermal fluctuations, you know. And so you go ahead and ask, where are these frequencies coming from? It's a circular membrane, so it's Bessel function solutions. You can solve this membrane, and this is the first order, second order, third order, and so on. And this is how the modes look like. So they match, except there are actually way more details in this than I can state in this thing. But an obvious thing is that there are the splittings in some higher order modes, and it turns out that actually if you go and we did this COMSOL simulations, it turns out that this graphene membrane is actually anisotropic, and whichever modes have an axis actually splits up because there is an anisotropic tension. And another very useful thing for this talk is that we also use this because it's a thermal motion, and under each mode, if you integrate the area under each, it's basically equipartition theorem. It has kT amount of energy. So we use that to calibrate this axis. So you can see these are already extremely small, like otherwise small displacements of the order of picometers. So this is the power spectrum density, picometer per root hertz. You can multiply to get actually the thing. So this is how we calibrate actually this spectrum. And this is the other part. If you remember, I was saying that there is a back gate, so you can actually apply a DC gate voltage, and when you apply that, graphene, of course, there's a capacitance effects, and you can think of what are the changes in the electronic level, but the mechanical effect is more interesting. It actually just gets pulled like a balloon. And this is exactly the way you would actually tune a tabla or a drum. You're basically tightening or loosening the membrane. So this is what we find. So what you're seeing, a cross-section of that will be this. So this is a fundamental split second order and so on. So what we find is as we increase the gate voltage, and please note the gate voltage because the spacing is like 15 micron. It's a very large gate voltage we are using to pull. And you actually see this dispersive behavior. There's a blue shift. In fact, some of them, there's a reason for that. Some of them first red shifts and then blue shifts. But there's also a very nice bit of physics. You see that as you increase the tension by putting the gate voltage, the displacement goes smaller, but temperature fixes the area under it. So as these peaks are getting smaller, you see it getting broader. Basically, the temperature remains constant. So that's about graphene, the small little thing, and it looks by itself very interesting. Its thermal motions are very interesting. What about silicon nitride? So we basically, go ahead, and this cartoon, you can see that this line is basically we just use photothermal excitation. So we come in with a side beam and just periodically, modulate it so it heats and cools. So as a result, basically the modes get excited, and we go ahead and probe on the silicon nitride. This is a hard measurement because already the displacements are small. In fact, our measurement noise flow is 200 femtometers per root hertz. So the silicon nitride, it's a heavier membrane, so its thermal motion is at 10.8 femtometers. Just to give you a comparison, the graphene thermal motion that we are looking at is 2-3 picometers. This is like almost 3 orders of magnitude smaller. It's a very, very tiny motion. We don't see that from our noise floor. By the way, we do not have a very good amplifier. If one actually in this same constraint can work better, can actually go down with this interferometer down to like 10 or 20 femtometers. So, and then what we find is that when we excite, we see these very discrete modes of the silicon nitride. They're getting excited, a whole zoo of modes, and they also remain unchanged with the gate voltage. This is exactly what we expect. If it's a heavier membrane, it's not getting pulled, so it doesn't buzz at all whether what the gate voltage you're putting. And these modes were very confusing, so we started putting, there are these packages, COMSOL, you throw in the numbers, it gives you the possible modes, and we basically find that, this is how the modes look like. They are actually very high order modes. So we actually looked at many different devices of different tensions, and so some are like 20 to 30, some are between 90 to 100. So extremely high order square membrane modes, and you see that a higher and higher order creates these beautiful coral-like patterns. But this is just for the reference, and the spacings are also not quite the same. So summary at this stage, we have just talked about 2 different oscillators. They are basically, there's silicon nitride, graphene is stamped on it. Both are, suspended. And this is the spectrum of graphene's modes, the energy spectrum. These are the silicon nitride. And you can see that graphene is tunable, silicon nitride is not. So if now I have this tiny, displacements which I'm driving, I can actually, if I want to see the interaction, I can try to bring a graphene mode by tuning the gate voltage in resonance with silicon nitride and see whether these two oscillators talk at all. So basically, given that these two oscillators, I have told the properties, the very important point of this cartoon diagram is, can I couple them? Can I actually hang one oscillator from the other? So that's basically the thing, that this is a thermal motion again of graphene. There's a Brownian motion, and this is standing here. And we know this dotted line is saying that when we drive silicon nitride, we know that the 27th mode of silicon nitride, there is a mode of silicon nitride. So we apply gate voltage, that's what I was saying. And when it comes there, we actually see this, splitting, or if you take a 2D plot, this avoided level crossing. And the splitting is basically the coupling, the physics is very similar to people who are in atomic physics, this EIT or this dark state physics that we're talking about here. I just find it personally very interesting that, because of this resonance, there are classical ways of explaining it, but also if you just look at it, the region where the graphene was supposed to be the most excited at the peak, it actually gets very quiet. And that's kind of the analog. But nevertheless, people have observed this in last 5-6 years, coupling between two resonators, and there are very fancy language people use to phone-on coupling, superposed states and so on. But actually everything you can just explain. This is classical, just a bilinear Hamiltonian of two coupled oscillators. You can solve them. It's really a undergrad problem. You can calculate the power spectrum, and this is the red line, and it fits very well. So that gives you all the factors you're interested in, coupling and so on. And another very important thing I forgot to mention is that the graphene is a bad oscillator in terms of quality factor. Its quality factor is 100, as opposed to silicon nitride, whose quality factor is many thousands, like 5,000, 6,000. So these are two very different quality factor oscillators. So, signatures of superposition, the question is whether we can have gain from this, and how strongly is the coupling. So I'll come to this strong coupling at the very end of the talk. How strong it is the coupling, and most importantly, how do I characterize what the coupling is. But anyways, that simple classical form, if you take, and if you look at the graphene's motion, you see that because of the coupling, very simple bilinear thing, there is a part which is silicon nitride, S and G stands for silicon nitride and graphene, and you see that there is a factor which depends on alpha, and more importantly, it inversely scales with the mass of the graphene. G stands for graphene. So this is what I was trying to show with that cartoon, that a low mass will really increase the contribution part of the silicon nitride. So that's basically what we measure, So this is, so we combine two measurements, one on graphene, one on silicon nitride. So this is on silicon nitride. You can see the scales. This is a linear scale. It really looks that dramatic. So the same, you are basically photothermally exciting graphene and photothermally exciting silicon nitride. You measure on silicon nitride, it's that. You measure on graphene, and you see this 38 dB of gain. And does it correspond to what you expect? This is the same expression for power spectrum. This is the gain expression. You can see explicitly that it scales with the coupling and inversely with the mass. In fact, if you put in the numbers, you expect more than 50 dB. So there's a huge discrepancy, not huge 40 and 50 dB. And we really think that in the mass of graphene we are putting single layer, but there can be contaminations, or it can be our collaborators are very confident that there are single layers, but they are also confident that there are PMMA and so on it. So so that mass we are basically underestimating compared to. And of course, a very important part, which presently we are very much into it, is the fact that this gain, a linear model really doesn't hold. Graphene is a highly nonlinear oscillator. I'll come to that a little later. So a very important point for amplification is sensitivity. That's actually a much more honest factor. It's basically saying that now whatever motion of silicon nitride you're looking on graphene, so what is the new noise floor of graphene, basically? Or rather, what is the smallest detectable displacement that you can see? So this is the noise floor on graphene. So SI0 is our measurement noise, and that's 200 femtometers per root hertz. This is actually, we are limited by the intensity of the laser. It scales linearly. Nevertheless, we have checked it's not really shot noise. It's actually a phase noise is involved in it. But the scaling is exactly like shot noise. And this is a thermal contribution. And actually, the thermal contribution of graphene is very large. So if this is what you see on graphene, you divide it by the gain. And that gives you what is the corresponding smallest displacement on silicon nitride. So you see that it's basically 28 femtometers per root hertz. So, poor man's amplifier, we start with a 200 femtometer per root hertz amplifier. We come down to 28 femtometers. We learn also many things. So this is a log scale of the same linear plot I was showing. So this is the graphene. This is the, this is our noise floor. This eventually comes there. This is the extracted silicon nitride, and you basically see that this peak is your signal, but there's this whole structure around it, and that's the thermal contribution. That's this. So there's a very large thermal contribution of graphene, and that's why, as Caves and everyone in 1980s pointed out, that it's impossible to have an amplifier. It's kind of another side of the no cloning, that it's impossible to have an amplifier that doesn't add noise. And here you see that the amplifier's noise is very clear. It's a Brownian motion of the graphene. So this is another thing. It's a combination of cartoon and measurement. So this is basically, we are looking at the quadratures. This kind of summarizes at this point what I have done till now. So these are X and Y quadratures for people who are familiar with quadrature representation of a harmonic oscillator. If you're not, it's basically, kind of going in a rotating frame of the oscillator itself. And there a harmonic oscillator is basically an amplitude and a phase. So these are these vectors. And this is how, so these are actually, these points are real points of fluctuations. So a harmonic oscillator will be just a vector. A noisy harmonic oscillator will have a scatter of points. So we started with here, and this is the silicon nitride noise, this yellowed points, cluster of points. And this is just electronic noise, or rather our intensity noise, because we don't see thermal noise. But when we have the gain, we see a very large gain, but also the whole cloud around it is the thermal contribution. So the question is, can we do anything about it? And there is a very nice, exactly the same ideas of squeezing that people do in harmonic oscillators. So, and this was for harmonic oscillators, people, like the first one was in 1991. The idea is very simple. So if you look at a harmonic oscillator, there's a, the acceleration term, the inertial term, damping, this is the spring constant, and the whole point of this parametric amplification is that you basically modulate a parameter, you modulate the spring constant at a particular frequency, in this case like twice the frequency. It turns out that the graphene actually is just, doesn't succumb to this, but it has this other terms, so this is, many might be familiar with this x cube or x4 nonlinearity in the Hamiltonian is this Duffing nonlinearity. But another very interesting thing of these nanomaterials, which was, I think, first time observed in 2011 or 12, is this nonlinear damping. And you see that very well in graphene. It's quite an amazing thing. So given that, we nevertheless, go ahead and basically put a frequency, a spring constant modulation, and that we can do very well because we actually have oh, this is just like some plots for the same system showing the Duffing-like hysteresis behavior. I'll just skip this. And in the phase and the amplitude both shows the same behavior for our system. But nevertheless, we basically go ahead, do this modulation by putting a AC gate voltage along with the DC, and we see this parametric gain. The interesting part is we are just measuring the parametric gain as in the power spectrum on graphene with the pump on VP versus without off, and we basically see that the parametric gain has very strong phase dependence. These are different values of the pump voltage VP, the amplitude. We see that there's a dip, a minimum and a maximum, and of course it increases. It's actually better to just look at these 2 points, the point 35 degree corresponding to the minimum and 45 degree corresponding to the maximum, and this is what we see that, one arm is going down and down, the other arm, very typical parametric oscillator behavior, the other arm is having a gain, and this region, it goes into self-oscillation. Again, like there are fancy ways of explaining this, that there's a phonon lasing mode. This is a 2D plot of that. You can see this very sharp intensity that, at that point it's self-oscillating. It doesn't care whether you have a signal. It doesn't care what it needs to amplify. It just is basically picking up from the pump, getting started from the thermal oscillator. So one of the things about graphene, though, is that this parametric modulation is highly, highly efficient. This is just a technical thing that if you remember this tuning or this thing, we are exactly putting a gate voltage, and because there is a 10 to 15 micron separation, so we had to put like 500 volts. And here you can see the parametric threshold is happening at 5 volts. So only a few % modulation. This is how the tension looks like. If you put everything for graphene, these parameters have very definite meaning. K0 is the intrinsic tension of the oscillator. So a mere 2% modulation of the intrinsic tension just saturates, it's highly, highly efficient. And that is because of the fact that, it's a highly nonlinear oscillators. People are already starting to observe many spectacular things. This is one of the nice things. But the most interesting part of this parametric gain, you're basically, it's like exactly like a swing. You're changing the length at twice the frequency. But the most interesting part of the parametric oscillator, which might not be trivial or undergraduate text, is the fact that actually the noise or the thermal fluctuations gets correlated in the two quadratures. And this is what we actually measure. So this was a graphene just thermal noise. But when we actually turn on the parametric modulation, we see that the fluctuations are actually getting correlated in the x and y quadrature with a very large fluctuation along this direction, and actually a squeezed, fluctuation smaller than the thermal one in the direction perpendicular to that. And this is basically, so actually they're squeezing on both the branches, both at 45 and 135. It doesn't, this is the overall gain, parametric gain, and this corresponds to the 135 degrees. So this branch here, and you see that this x1 and y1 are these two rotated quadratures, and this is the standard deviations or the variances, and you see that one is actually getting broader, the other is actually going and saturating, and you can ask the question, where is it saturating? It is actually saturating because of KT, and then you can show that there's a factor of 2 you can do best. So there's a a 3 dB limit in standard deviation or 6 dB limit in variance, and that's what one achieves. But also this is not the only limitation. One can actually put a very, very simple feedback and take it down to like 12, 13 dBs. It was demonstrated in 2014, actually. I should have Vinathe's group, actually. Vinathe. So I'm 5, okay. So the sensitivity comes down to 17.15 femtometers. So this is the final amplifier noise budget. You have 5 minutes? 5 minutes, okay. So not so bad. So I have the noise budget of the amplifier. This is the final thing that this is the noise which sets the sensitivity, which is also called the imprecision noise. There's also a noise because if I look at the silicon nitride, there's exactly the way I was describing the gain. It's a bilinear system, so there's also graphene coupling back to silicon nitride. That's the back action, basically. And you see that the back action scales. This is just a back action just coming from the thermal forcing of graphene. It actually scales inversely with, here, the graphene mass. So actually, the small mass of graphene is producing a huge back action. And what we estimate for our thermal forcing is about like 37, 40 femtometers per root hertz. And it's quite a thing. If you think of it like it's just a 15, 20 micron atomically thin drum is pushing like something like 350 micron, 300 nanometer thick, huge object. It's still giving a very appreciable pull. And we basically, like when we put the imprecision noise, if you see that it scales inversely with the gain, which scales as alpha square. So this actually goes down with alpha square. This is the coupling, and this actually goes up. So you see that there's a critical coupling. When actually the back action and the imprecision noise are balancing, we are slightly higher than that. So this is the point I was promising in the beginning that the word strong coupling, again, is a word which is a very loaded word, and it used like left, right, and center in different meaning. Sometimes it's in context of cavity QED, sometimes it's just because you saw splitting. Here, this is how we are actually, like I'm stating the strong coupling, that this critical coupling would have been enough, but we are stronger in the regime where we are basically dominated by back action. So, so there are different ways of reducing it. One very beautiful thing about graphene that over last 12 years of its discovery, people have really like perfected this thing. So you can actually like go to a fab person and he or she will make like, 1 layer, 2 layer, 3 layer, 4 layer, 10 layers, 15 layers. So we basically find that there is actually, in terms of mass also, there is a critical mass depending on your coupling. So, you can actually, like, we are so back action dominated because of the fact that the mass is very low. You can actually make the mass heavier and that way bring down the back action force. So this is kind of, number of layers versus that plot. So with that, the first promises that tunable, we are saying that it's a tunable resonator as opposed to all the other like point contacts and so on, which are like on resonate, very narrow band. So this broadband, I didn't talk much about it, but you can see the fact that the quality factor of graphene is bad. The fact that it's 100 is the quality factor. It actually goes for advantage as an amplifier. It is spread over broad regions. It's strongly coupled. There is the sensitivity. There is the group. Just 1 minute. This is not the only thing we work on. We also work on like cold atoms. Like we have a cigar-shaped MOT, DLCZ-like correlated photons. So we are just starting to measure like very strong quantum correlations. We recently finished a work on quantifying coherence experimental work. This is something we are, in fact, I was debating today morning whether I should actually talk more on this for this crowd. So this is actually in archive. An earlier version we published 2 years back, but the thing is we just put last month. And eventually, really our aim of our group is actually, it's not really disconnected experiments. These are great oscillators, and over like next 4 or 5 years, we really want to make an interface between atoms and oscillator. So with that, I'll finish. Thanks for the extra. Thank you.
The kind of Brownian motion that you have addressed is still thermally driven. Right?
Yeah, I'm calling it Brownian because it's thermal.
Yeah. But there is also another kind of Brownian motion that can happen as you keep lowering the temperature. This is driven by quantum fluctuations. And 0 point
well, I'll not call that Brownian here. So that's basically you're talking of 0 point fluctuations, kind of. Or,
yeah. In fact, I would call it Brownian because.
Well, I'm calling it in terms of what Brown observed. Like so that is the thermal fluctuations. Yeah, but yeah, 0 point fluctuations.
Because, there is quite a body of people who work on quantum Brownian motion, where they
absolutely.
study the
that way your quantum Brownian motion.
Interplay between thermal fluctuations and quantum fluctuations.
Yeah.
So as you go to lower temperatures, cryogenic temperatures, you would see.
Absolutely.
So the thermal fluctuations don't really set a limit. As you keep
no, absolutely, yeah. So all this calibration,
So what I was saying is just it would be interesting to see how the nature of noise changes as you lower the temperature.
Yeah, as far as this work is concerned, in fact, one can estimate everything that I was talking about in terms of calibration, the noise floor, S thermal of graphene, which was dominating, which is because of KT, it basically just gets replaced by half h bar omega. So it's a 0 point motion. And there's an interplay region, of course, which is much more interesting.
We have done some work on quantum diffusion law, so we can discuss.
Yeah, we can discuss that, yeah.
Any other questions? Yes.
Saikat, duffing anyway produces a very nice arena for, from a dynamical systems point of view, bifurcations and limit cycles and so on. Would you envisage trying out any of that?
We are actually, all these results I'm showing you are like 6 months old. We are still just polishing things, but over last 6 months we are just looking at those things, and it's like the kind of things that graphene starts showing is very interesting. It will be nice to talk to you, but there are all sorts of different kinds of mixing, wave mixings, and you see a whole stream of new wave components being generated. There are also very interesting things. We see, for example, that silicon nitride, which is a very linear oscillator, picks up nonlinearity because of its coupling, on resonance because of its coupling, and this limit cycles and this different.
There's a nice bifurcation scenario also.
Yeah. So we see all that, but it's like a little too complex because of the fact that there's also this nonlinear damping along with duffing, which is playing a role. So it's not usual duffing, and but those are very, very interesting points.
Thank you.
Yeah.
Saikat, yours is a phase-sensitive amplifier. I see that because so if you have a small modulation in your silicon nitride, it obviously preserves the phase in the graphene as well. So there's something called a noise figure which captures the, input-output noise. I mean,
Yeah, we didn't look at the noise figure. We are quoting it in terms of the sensitivity.
okay. Do you know, happen to know what?
I can tell you right after. This is basically you're saying the two ratios of the circle versus this thing. We just look at the the sensitivity, but yeah, we can just talk.
Very interesting work. Now you also told us about back action and how the tail wags the dog, so to speak. So, and you also showed initially that in your sample you have a number of these membranes. So, have you explored what happens? Are the vibrations in the membranes coupled? Can you?
It's a very, very interesting question. In fact, yeah. So, something like this maybe. So, yeah. So, yeah. So, for example, like this and that membrane.
Yes.
So through silicon nitride, they might get coupled, and it's not that we explored, but we saw this signature, which was for months we thought it's artifact. We changed every possible BNC connectors, everything, and then just it happened that at some point we moved to the next drum and we found that where the artifact is the resonant frequency of that drum. We still don't understand, the whole mechanism, but it's true that silicon nitride can couple the two graphene resonators.
And just to get an idea of the experiment, I presume all this is done inside vacuum? Or
yeah, but we have a pretty bad vacuum. In fact, we should have improved, but things are happening and we have not opened it. The vacuum is basically very rough, like millitorr scale. Just a roughing pump vacuum. We don't even have a turbo.
Thank you.
And of course, the quality factors will improve if we can improve the vacuum.
Thank you.
About the discrepancy in the gain calculation, which you attribute to the probably imperfections in graphene production. So I was just wondering that you calculate the thermal fluctuations using equipartition. And in this model, I mean, it's a pretty small system given the number of atoms in that circle. And there are boundary conditions because it's a coupled oscillator. So I would suspect that you would have to consider correlations between the modes, like the Brownian correlations between the first, second mode.
For graphene itself?
Yeah, and equipartition would just tell you that they're uncorrelated, but I have fluctuations of individual modes.
Well, yeah, that's also a very important point. So there are correlations. In fact, you actually see intramodal transfer, but those are actually highly nonlinear effect, right? Like wave mixing between modes, and that usually doesn't happen at the thermal amplitudes because those amplitudes are very small. So you need to push it a little.
But what I meant is, although the temperature is small, the system size is also small. So usually the temperature which is relevant for setting of equipartition is decided by.
Temperature is not small, by the way. Temperature is room temperature.
I assume that
this is all room temperature.
Oh, okay.
All the measurement is room temperature.
Okay.
Yeah, but anyways, you can make the point you are making.
Thank you.
No, you're saying something, no?
No, I just thought maybe the temperature is also small.
I see. But just regarding the gain discrepancy, it's true that the mass we are underestimating, it's not a single layer. But we are pretty convinced that this bilinear modeling is okay just for a guide to set up the experiment. But it's really the duffing, like we basically, when we are amplifying, it's at 300, 400 picometers of amplitude. That's a massive amplitude for graphene. And there it's, the duffing, the linear oscillator, the gain will saturate.
In fact, that's a further point because duffing is a cubic term and equipartition usually assumes a quadratic interaction.
Yeah, so I have I don't know how to think of equipartition in presence of duffing. Okay. Absolutely, yeah.
But actually, there's a reference I could.
But the only thing is that the equipartition we use only in case of thermal motion. Again, there is no duffing issue, because the amplitudes are very small.